The last topic to look at in section 3.9 here is the idea of approximation error. And the overall idea here is that errors in measuring one quantity, so errors in measuring, let's say, X, can lead to other errors, so lead to more errors if you use that X value in certain calculations. So errors in measuring X can lead to errors in the calculation of Y or some other quantity. Okay, that's the main idea. So let's look at this in terms of a problem. All right, a surveyor is measuring a square lot. The lot's side length is 300 feet with a possible error in measurement of up to 0.1 foot. What is the maximum error in calculating this lot's area? Okay, so the idea here is that, if we have a little error in measuring the side length of this lot, that could lead to errors in the calculation of the lot's area. And this is not any fault of the surveyors necessarily. We are only so accurate as our tools. So maybe this guy's measuring tape is only accurate to within 0.1 foot. Or, in chemistry, your scales that you use, your balances for weighing out chemicals, they have some sort of error tolerance on them. Maybe they're accurate to 1/1000th of a gram. Maybe they're accurate to just 1/10 of a gram. Or maybe it's a really sensitive scale and it's used for measuring things on like the nanogram scale. We are so accurate as our tools will allow us to be. So let's look at what's going on with the surveyor here and his measurements. So we want to set up an equation for calculating this lot's area. And it is a square lot with, we'll say, sides of length x, okay? And so the area of this lot is just going to be x squared. Very exciting. Okay, now how we can look at this is with using differentials. That's why this is in section 3.9. If we take the derivative of this equation here, dA dx, the derivative with respect to x, is just going to be 2x. So we're taking the derivative with respect to x on both sides. And we could turn that into a little differential, okay, for dA. So dA is going to be 2x dx. And with these differentials, the little changes, the little dA, dx, those are referring to little errors in our measurements. So the dx right here, a little change in x, how far off could we be with x? That's our error in the side length measurement. And so similarly, dA, little change in A over here, that's a little error in the area measurement. Okay. And then X here, of course, is the side length. So that will have an effect on this differential as well. Okay. So if we want to calculate dA, the error in measuring the area of this lot, we would do dA equals 2 times x, which is, side length is 300 feet. Okay, 300 feet there. And then times dx, the error in that side length calculation. And we want to max this out because we're looking for the maximum error in calculating the lot's area. So the error can be up to 0.1 foot. Let's max it out. Let's put the full 0.1 foot error in that. So 0.1 foot that we could be off. Okay. And so if you crunch the numbers on that, that's 600 times a tenth, so that would be 60. And the units on this are in feet times feet, that would be feet squared, which makes some sense in looking at area. So 60 square feet is the maximum error in calculating this lot's area. Now, you might look at that and say, kind of from one camp or the other, either, wow, that's a lot of error in the area. 60 square feet is, you know, a reasonably sized room. That's like a 10 foot by 6 foot space there. That's pretty significant. Or you might say like, oh, 60 square feet is not that much. Like, that's not that big of a room. So you're probably in one camp or the other there. And, you know, the reason why you can really go one way or the other with that, I guess, is because we don't really have much context for this measurement. And so the idea with that is that there are going to be different ways to express error. And all that we're looking at here right now is what we would call the absolute error. It's just the number itself. Absolute error, or you could call this an absolute change in area. Okay, so this is just the raw value. Oops. From calculating dA there. Okay, so dA equals 60 square feet is the absolute error. Okay, now the next way we can look at error here is to make it relative to something else. And so this is called relative error, or sometimes this is referred to as a relative change. Okay. And we calculate this by taking our absolute error. So absolute error in our measurement relative to how big that measurement actually is. So that's divided by the total measurement. Okay, so our relative error for the area here, let's note that, relative error for the area is going to be our error in the measurement, so that would be dA, over the total measurement, which is A itself. And we could put numbers in for that, sure. But first, let's look at it with some variables. Because we found dA, an equation for that right here. dA was 2x dx. Let's put that in right here, 2x dx. And A, the formula for A itself was just x squared. And so if we simplify that a little bit, we can reduce down, cancel an x there. You'd have 2 dx over x, which could also be written like this, 2 times dx over x. And that little dx over x there is itself a relative error. Okay, that's the error in measuring the side length over the side length itself. Okay, so this is relative error for side length. So that's kind of interesting that you can spot the relationship between those two so quickly there, so nicely. If you want to find your relative error for the area, it would just be twice whatever your relative error for the side length was. But if you're wanting to just find this in terms of numerical values, we would take dA over A and put in what we found there. So 60 square feet for dA. And then we would calculate the total area based on our surveyor's measurements. So the side length was measured to be 300 feet. So our calculated total area would be 300 feet getting squared. Okay, so you'd type that in and you'd get 6.7 times 10 to the negative fourth, which is a pretty small number. We'd have 6.7 and then move that decimal place back. 1, 2, 3, 4. 0.00067 for our relative error. And so that doesn't sound quite as bad as 60 square feet. Relative to the size of this lot is pretty large. Let's see, that would be 9 with 4 zeros after it. 9, 1, 2, 3, 4, 90,000 square feet for the size of this lot. 60 square feet out of that is not a huge amount. Okay. So that also leads into our last way of expressing error here, which is as a percentage. Okay, so this is percent error or percent change. You can also see this referred to that way. And how you calculate this is you take your relative error. So you have to use that previous calculation. And then you multiply it by 100 to make it a percentage. Okay, so here our percent error in area is going to be our relative error, dA over A times 100. So we'd take our 0.00067 times 100, and we would end up getting 0.067% for our percent error. And personally, I think that's a really nice way to look at this particular problem in terms of error. That 60 square feet, our potential maximum error for this surveying of this lot's area, 60 square feet. Initially, that sounded like a lot to me because, I mean, that's a significant portion of my house. So 60 square feet sounds like a lot, but relative to the size of this total land parcel, it's only 0.067%, so less than 0.1% here. So in that grand scheme of things, this error doesn't actually seem that huge. So that's why it can be useful to have different ways of looking at error.